So welcome to lesson 5. This is about this fellow here, which is the origin, or the point 0 and 0 in the x and y axes, and in fact 0 in the z axis as well. We are currently going to find out which layer this is on. Of course it's on the layer grid, so let's just go to the layer grid and we'll have a look at that. You recognise this block of flats here, and of course this is a 3D top view which is rendered in OpenGL. We'll just go to there's our 2D view, and there is our 2D view just of the grid of that plan. So, well, just first of all to note, it's we call it a compass. This is compass for this job, and x is 0, y is 0, and z is 0. Let's have a look at it. What's the point of it? Well, the point of it, you'll see here, this is the internal origin 0, 0, 0. That's Vectorworks' default internal origin, and it affects things like when you're making extrudes and stuff, when you edit them, that the primitive stays in the right place. So the best thing is to have your user origin the same as Vectorworks internal origin. This button here, user origin, there we are. And are you sure you want to change the user origin? Yes or no? And in fact I don't, because there was, it seems to have gone. There's a menu for setting that origin when you need to do it, or you use that little button. Now, so why is that important? Okay, I'm going to cut that. I'm just going to paste. Oh, it's there, right? It's no longer in 0, 0, 0. So this most incredibly useful command is paste in place. Paste in place puts it back with the coordinates where it was cut or copied from. Let's do that. So I'm going to cut that. We'll go back somewhere remote over here. Well, that'll do. Now paste in place. Whoops, it's not there. It's gone back into the position it was, 0, 0, 0. Now, of course, that's fantastically useful. It means that you can copy and paste bits of plan if you've got separate files for your first floor, second floor, third floor, roof, blah 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 blah, or your site plan. When you copy and when you paste, it goes back in the right place, and particularly when you reference, or in AutoCAD speak, when you xref another file, mechanical overlay, electrical overlay, structural overlay, whatever it is, it'll go in the correct position. So at the beginning of a project, you want to try to persuade your esteemed consultant colleagues, mechanical, electrical and structural engineers, to agree on the position of this important origin. In fact, in AutoCAD it is called insert base. You might persuade them. I haven't ever, actually. But so you just have to live with that. When they send you an AutoCAD file, you just draw a circle, find out where its origin was, is or other, and often it won't be in the same relation to your plan. So it's a chore, and often your imported AutoCAD overlays, they will be different within different issues. A structural drawing sent to you in May may have a different origin from the one they send you in July. So the grid is important in order to determine the how to overlay, how to reference that in. You have to make your own file, set it up with your own origin, and then you can use it, and it seamlessly imports into your own drawing. Anyway, that's it's a chore. So the grid is useful for that, and in particular, we'll look at this. This is a grid line. Okay, well, you'd expect it to be 180 degrees to 6 decimal points of accuracy. That's terribly important. If the grid is out, a small fraction of a degree over the distance of an entire site, which may be, say, 100 meters, gives an error, a significant error. Very often you'll find that a grid, or the drawing in its entirety, does not have sufficient angular accuracy. It might say it's 180. When you crank up the angular accuracy, I recommend at least, well, 6 decimal places. When you'll open a file, you'll find it's got 1 decimal place of angular accuracy, and when you crank up that to 6 decimal places, you'll find that line is no longer 180. It's 180.0479, and that can make a big difference. So please make sure your angular accuracy in particular is 6 decimal places, and it's obviously working in millimeters. But not that matters. So why is this important? So let's have a look at something that you might get from a consultant in the design team who's working in AutoCAD. Whether they're skilled in 3D modelling, there's great virtue in the 2D drawing. It's an overlay, it's a diagram. So, and there are things that we don't want to model in 3D, like, no one's going to necessarily, well, no one in their right mind is going to model a screw and a nut, or something, a minute detail, unless it's in a 1 to 5 detail drawing. But in your GA plans, you don't want that. So unfortunately, you may have the misfortune to receive something like this. It's a whole bunch of sections of a big and quite complex building. You can see what's happened, and in the days when we used to use a drawing board, in order to change the projective plane projection from plan to section, we rotated the piece of paper around so that the drawing itself remained horizontal on the table. What's happened here is that they've rotated the table in order to cut those sections through the complex plan. Secondly, you'll notice that these are huge numbers along these X and Y rulers. And why is that? So what's happened here is that the drawing is geo-referenced, basically, and it's miles away from the origin. This is really important. Apart from the fact you can't work with it, it affects the accuracy of hatches and various things. And so our origin, a slightly different marker here, it was a job that we did a few years ago, but you can see there is that is 0, 0. So this drawing is actually about 9,000 it's 90 kilometers away. Because that's the geo-referencing according to the actual geo-reference location of the site. How can you work with that? I mean, A, it's hopeless, and B, it eats into your productivity workflow. We're trying to make a way of taking a plan with a complex plan. What's important for cutting sections is that your datum 9 is your y coordinate, right? There's 0. This is plus 150,000 millimeters. This is sea level, so it's actually 1.6 kilometers above sea level. So this is an example where the y-axis is exactly the site datum above sea level, and this is what we used to do with the drawing board. Your sections and your elevations are in a line. So my datum is consistent. I can check that the parapet height is the same in all the sections, for example, or floor levels and all the rest of it. That's the way. That's the way you do it on a drawing board. What gives the position of the sections? Why aren't they? Okay, let's assume that they're at least in a horizontal line, coordinated. That is the word, coordination. And so what sets this position? Well, clearly the plane projection from the grid. So in fact, this is the position. This is the position of the base grid drawing. So there's north, east and west, and that is its true orientation in the grid. And if I project this grid, of course, one of the grids is orthogonal to my page. We've arranged it so that one of the grids is orthogonal to the page. So we have in fact rotated the origin to suit our purposes. There we are, and here it is. Its grid south is horizontal.